Last class, we discussed the damped driven pendulum and we solved numerically the damped driven pendulum. A few of the things that we looked at, I listed on this side. One was isochronism versus non-isochronism. The fact that the period of the pendulum or the frequency of the pendulum is constant or independent of the amplitude of the oscillations and the mass of the pendulum for small oscillations. So that's isochronism. And then non-isochronism is the fact that the period of the pendulum, natural frequency of the pendulum, is not constant, independent of the amplitude of the oscillations or the mass of the pendulum if the oscillations are large. So that was one kind of really important feature of the pendulum. We also talked about damping. We talked about this world, or these two extremes of underdamping and overdamping, in which you get oscillations and not oscillations. So that's another important sort of branch or class of pendulum motion. And then finally, we talked about a driving force, adding a driving force. We added sinusoidal driving forces. And we explored the world of resonance. If the natural frequency of the pendulum is nearby the driving frequency of the driving force, then we saw we could get resonance. Resonance being large amplitude oscillations away from the natural frequency. The driving frequency will only cause small oscillations. That's away from resonance. In today's class, and actually the next class is, we're going to work towards exploring chaotic motion, chaotic behavior for the pendulum. To explore chaotic motion, chaotic behavior, I want to introduce two further ways of visualizing pendulum motion and plotting pendulum motion. So in the last class, we just plotted the angular coordinate of the pendulum versus time, theta versus time, where we plotted the angular velocity of the pendulum versus time. So we had omega versus time. We're going to add to that those ways of plotting, visualizing the pendulum, two more ways. One is phase space diagrams, and the other one is Poincare plots. This class, we'll look at the phase space diagrams, and next class, we'll look at the Poincare plots. These are two tools that will help us and aid us in exploring chaotic behavior. They allow us to explore the world of chaotic behavior in much more detail than just plotting the angle of the pendulum and the angular velocity of the pendulum versus time. So that's why we're doing that. So that's the overall plan. You can create chaotic motion with a damp-driven pendulum if the driving force, the amplitude of the driving force, is large or strong. What that means is that the amplitude of the driving force, large or strong, is large or strong with respect to the other force, gravitational force. So that's the condition that pendulum motion will show chaotic behavior. And that's the corner of this problem that we'll be exploring, the case of large driving forces and the parameters of large driving forces, their amplitudes and their frequencies. So phase space trajectories, what are phase space trajectories? Well, phase space allows you to, permits you to completely describe the motion of the pendulum. It provides a complete description of the state of the pendulum. And for the pendulum, the phase space is these two coordinates, theta and omega. So phase space for a pendulum, damp-driven pendulum, say, is a two-dimensional space of theta and omega. And that's the world in which the pendulum lives. And that space of theta and omega is the world in which we can plot out the motion of the pendulum. So that's what we mean by phase space. The trajectory of a pendulum is a trajectory in this two-dimensional space of theta and omega, of angular position and angular velocity. So we're going to make these plots of angle versus angular velocity. The initial coordinates of the pendulum, when you release it, those theta naught and omega naught are the complete description of the initial coordinates of the pendulum, the initial space of the pendulum, that allows you to project the future trajectory or a path of the pendulum. So that's what we plan to do. This is a language that we're going to do it in for the damp-driven pendulum. This is the language we basically used in the last class. I just repeating it here to remind us here. I wrote down here, though, the version of the second order differential equation that's independent variables time, dependent variable is theta. I wrote it in these two different kind of equivalent ways. This one using G over L, which describes the pendulum. This second version here using the fact that square root of G over L is omega naught. So G over L is omega naught squared. So this is another way that we can write the pendulum. Either is fine. Maybe this way here you see what is the world, the parameter space of the damp-driven pendulum. Well, the parameter space of the damp-driven pendulum is the angular frequency, natural frequency of the pendulum. That's one parameter. There's the driving frequency of the driving force. That's a second parameter. So those are two frequencies in our problem. And then we got two strengths associated with two forces. There's the damping force, so that's the beta in our equation, and then there's the gamma, which is the driving constant in our equation. So that's a list of four parameters that completely describe our damp-driven pendulum. It's sometimes handy to remember the kind of the units of these parameters. In fact, you know, omega naught and omega f obviously have units of frequency, but the damping constant beta also has units of frequency. So all those quantities have units of frequency, and you can see it by just thinking about the fact that the units of every term of these four terms in the differential equation obviously must be the same, and must be inverse second. If you just think about this as radians per second squared. So out of that drops off the fact that omega naught, omega f and beta are all have units of inverse seconds, and gamma is unitless. If we were to switch off beta and switch off gamma, put beta and gamma to zero, and approximate sine theta for theta, then that's simple harmonic motion. Okay. So let's start looking at phase space plots we'll start with the case of the undamped, undriven pendulum, the simplest case. We'll make a phase space plot for that. And then we'll look at the damped pendulum without driving force. We'll make a phase space plot for that, or plots for that, explore that. And then we'll move on to the damped driven pendulum and make phase space plots for that. I think I'm going to just do all of that in my code. I put one more code in my physics 508 subdirectory. Where are we? This, oh, I already opened it actually. Here it is. So here it is. It's actually just the code that we used in the last class, but I've just added the plotting for the free space plot. So in this code, I'm going to plot instead of just theta versus time for the pendulum and omega versus time for the pendulum. I'm going to add the phase space plot so we can see those, and we'll just work our way through from the simple motion without damping, without driving forces, to the more complicated motion with damping and driving forces, and bump into chaotic motion. So let me just remind us, I should make this larger. Is that large enough? Or do we want to do one more? Okay, this is the cell where we really define the guts of the code, the two user functions that solve the second order differential equations. So the RK4 method based on fourth order Taylor expansion for solving ordinary differential equations, and then the specification of our differential equation. It's a second order differential equation, but we remember the numerical procedure always breaks it into first order differential equations, a pair of first order differential equations. In this case, one of them just being the fact that the differential of the angular position is the angular velocity. So that's one of our differential equations. And then the second one being that the differential of the angular velocity, which is angular acceleration, is this sum of three contributions to angular acceleration. One arising from a restoring force, so that's the upper one here, that contributes to changing the angular motion, angular acceleration. One arising from the drag force, that contributes to the change in motion, provides an angular acceleration. And then one is the driving. There's the transmitting and driving force. Okay. So I won't say any more about that because it's exactly the same cell as before. Here's where we set up the space in which we're going to work, or the time in which we're going to work, discrete time. When I went ahead and solved this problem, I made a time interval of 100 seconds to watch the pendulum for. I made 4,000 ticks over those 100 seconds. So I guess that's 2.5 milliseconds per tick. So those are the first few lines here. Then I'm setting up the parameters of the pendulum here. I'm going to, for all these examples, and I think in the associated assignment, I picked a pendulum that is 9.8 meters long, so that the natural frequency is there, which is the square root of G over L, is going to be the square root of 9.8 over 9.8. It's going to be 1 radian per second. So this is a almost 10-meter long pendulum, very long pendulum, that slowly swings backwards and forwards with a frequency of 1 radian per second. So it's going to take 2 pi seconds to complete one oscillation. So over 6 seconds for an oscillation, to and fro. So it's going to swing back very slowly because such a big pendulum, and compare that to the 100 seconds that we're observing it for. So, we might be seeing 15 or more oscillations if it was just undamped and undriven. So that's the pendulum. And ultimately, the G and the L are just defining omega naught, which is going to be 1. And then we've got the other constants that we're going to work with, which is beta for the damping constant and gamma for the driving constant. And then, yeah, I got beta and I got gamma, and that will be, those are the complete set of parameters for the problem. I want to start this off with a undamped situation and an undriven situation. So I'm going to just set these constants here, beta and gamma, to be 0. And so that's turning off the driving force, that's turning off the damping force. So that's what I've done here. I did also, I'm defining it here. And we're going to play around a lot with this. I defined here the driving frequency. So this is a number I'm going to play around a lot with once we switch driving on. I'm going to start it at a frequency that's very close to the natural frequency, so that would be essentially on resonance for the natural frequency. But right now, as you see, because beta and gamma are 0, there will be no driving term. I'm going to print out, just for reference for us, what the driving frequencies and the natural frequencies are, because a lot of this is going to be about comparing those two so that we can see them, just what the numbers are. So that's the printout there. I'm going to start all of these with small oscillations, pretty small oscillations. So theta naught, I'm just displacing the pendulum by about 5 or 6 degrees and then releasing it from there. So omega naught is 0. So we're going to do that. I think we did that most of the time in the last class. I need to define the proxy for the dependent variable, independent variable. So that's T. And so this is just an array of finely spaced ticks, 4,000 over 100 seconds. I need my proxies for the phase space coordinates, we're now calling them, the theta and the omega. So I'm defining that proxy, that meta variable, as this n/2 array, where there's n rows for all the times, or the ticks, and then there's 2 columns for the theta coordinate and the omega coordinate, and that's exactly what we did before. I set up the initial conditions for my coordinates, and then the whole work is done by this line here, this pair of lines here, where in a for loop, I take the current values of theta and omega stored in this variable that I'm passing here, and calculate the future, the value, the next check the value for them. And I just do that over and over again. Maybe I should make a remark about the indexing I'm putting on here, because I've got theta G plus 1. So this is J is an index for the tick. So it's the J tick and it's the J plus 1 tick. But there's something a little bit more subtle going on in the background here, because as I mentioned last time, I'm really passing this quantity here is a 2-element variable. It's got omega and theta embedded in it, and this quantity over here is a 2-element variable. So this this slicing with J, what does that mean? Because I've got a two-dimensional array. I just put J, what am I really doing when I'm slicing? So what J means is if I was to write that out in full, what that slicing means. Because I've got a two-dimensional array, it means that I'm slicing out a particular row, so that's the J. And then I'm slicing, I'm taking both columns. So I might have written it kind of like this. This J here is equivalent to this guy here. It's a slice of a particular row, and it's taking all the columns. So that's what I'm doing here. I could have written it even, just to be more specific in terms of slicing. I could have written it like that. So that's where I'm being really specific about the slicing of the rows and slicing of the columns. So it's a little bit misleading there, where it just kind of looks like I've compacted it.
Could you instead put J plus 1 on the left equals J by itself? And then cool.
J plus 1 on the,
Like within the brackets and then equals J or colon. Could you instead go with that, or that be?
well, this bit here is just this slice, right? So this is a way I could have written that slice. Are you saying because there's another slice like this on the left-hand side where I've got that? Yeah. So that would be like J plus 1, J plus 2. It would be like this. It's the long way of writing that. Eventually, the long way of writing it doesn't kind of become misleading, but it becomes passive.
So is the just the colon by itself, is that implicitly like 0 back to 0? Or is it 0 to, there's like, if you were explicit about that slice, would it be 0 to the last or 0 back to 0?
Here, this notation, it accepts this as the row. If you just put one index here, it's going to denote the row. There's not an equivalent to do the same thing for, supposing you want to slice a column. I'm pretty sure you'd have to do comma K, that you wanted to slice the comma.
Okay.
And comma K plus 1. So it's not symmetric between rows and columns when you do this slice.
Okay, thank you.
Or at least the shorthand is not symmetric, right? If you write the long thing out, it's completely, the same for a row and a column, but the shorthand is not symmetric. Okay, so we were just explaining that detail in this little bit of code, which could be confusing. I think that was the idea there. So I come out of that for loop and I've got theta, which is this n columns, n rows, 2 columns, where one column is theta and one column is omega, and I'm gonna I want to separate out the theta and the omega into 2 one-dimensional arrays that are going to be proxy variables for theta and omega versus time. So that's where I am doing this slicing here. And again, so here I'm slicing out the first column with the theta, keeping all times. And I could have written this just square bracket comma 0 without the colon here. And this one here is square bracket comma 1, which would slice out the second column. So that I could have written that shorter too. I wanted to say a word about the copy here though. Because the code would also run if I didn't put the copy in there. So what is the reason for the copy, or why might I put the copy and why might I not put the copy? If you put the copy there, it creates a new variable at a new location in memory of the computer and copies the data into that new memory location in the computer. So if you have a copy here, you have the old variables, theta, that we're copying from, and then you've got the new variable, or variables that I call theta underscore n for numerical, omega underscore u for numerical. So it's like I've got in memory theta, which is a n by 2 array, and in some other region of memory, I'm making these two other arrays. They're both one-dimensional arrays that are theta underscore n, omega underscore n. What that means is that I could later on like tinker with theta and it wouldn't change theta underscore n and omega underscore n, or vice versa. So I could change one and it wouldn't change the new variables. And that's because I copied. If we didn't have copy here, what Python will actually do with these numpy arrays is just make the variable theta n point to the same location as where this array theta is starting. And the variables omega n just point to the location of where this array is starting. So it doesn't make a copy of the doesn't give the new variables their own copy of the original array. Rather, it just associates with the new variables with the new array, with the old array. So if you don't use the copy and then you go on and change the thetas, you'll change the thetas underscore n's and omega underscore n's without realizing. So that's the danger of it. So that's why the copy is there, just to, you know, so that they are new variables with their own copies of the data. Okay. I think I wanted to explain this. The theta underscore n, omega n underscore n, the underscore n's I just put in because they're the numerical solutions of two variables, and I wanted a name that was different from the theta. That was the meta variable that contained the theta and the omega. This is meant to be theta underscore n prime. By that, I meant that in the examples we're going to do today, we'll see that the pendulum will loop the loop. So it'll go swing so with such large amplitude, it'll go over the top, and it can go over the top in kind of a clockwise direction or in a counterclockwise direction, in directions of increasing or decreasing omega. So we're going to get the loops, the pendulum that we didn't have to deal with in the last class. So when we get a loop the loop, suppose we kept getting the loops in the counterclockwise direction or the clockwise direction, we would, every time we loop over the loop, that's completing 2 pi. We'd be incrementing omega or decrementing omega, theta in units of 2 pi as we loop the loop. If I just wanted to look at the coordinate theta within a range of 2 pi, then I might divide by 2 pi and take the remainder. So that would just give me the coordinate on kind of the complete circle of the pendulum, and won't be counting up, incrementing the loops that occur if it goes clockwise over the top or counterclockwise over the top. So that was the idea of this. Theta as it stands, theta n as it stands, can be any value, right? From 0, the equilibrium position, through positive pi, where it would run over the top of the pivot point, through to 2 pi, 3 pi, to an infinite number of pi's, right? It could be any negative value from, if it went the other direction around, from negative pi, when it's going to go over the top of the pivot point, to negative 2 pi, 3 pi, 4 pi, and so on. They go infinitely far in the negative direction. So I've made a new variable that is just the theta coordinate divided by 2 pi and the remainder of that division. And I did that, so I have a coordinate which is just a coordinate for the theta between minus pi and pi, where 0 is the equilibrium position, and minus pi and plus pi are the extremes of the motion. And I've taken theta again. I could have written this as theta n, actually. I added pi on. So to make, so to do that, I added on pi. So that would take my equilibrium position to be 0, from 0 to pi. I added it on, I then divided by 2 pi, got the remainder, and then subtracted off the pi and afterwards that I added on. So I put on this offset of pi, divide by 2 pi, and then subtract off that offset. And that keeps the equilibrium position of the pendulum as a theta of 0, and the extremes of the pendulum of minus pi and pi. And I think you'll see that on the plot. So that was the idea there. This is just analytical solutions of a simple pendulum without the damping and the driving. I think I didn't really need that. I could remove that. And then I'm going to make my plots. So I'm going to make 3 plots this time. So I've got 3 subplots. This is me. I'm going to have to make it smaller here. It is the size of the entire figure. And here are the 3 plots I'm going to make. So I've got the upper plot will be theta. The center plot will be omega versus time. So theta versus time, omega versus time. And then finally, this is the new guy. This is going to be the phase space plot. That's going to be the bottom plot. A couple of remarks about it. When I plot theta versus time, I'm actually going to plot 2 curves. One is the theta that can go from 0 to positive infinity or negative infinity. One where every time you loop the loop, you're going to be adding or subtracting on 2 pi. So that's one of the theta curves, and that's going to be the blue one. And then there'll be a second one where I'm just plotting theta between minus pi and plus pi. So anytime it loops the loop, it won't increment by 2 pi or decrement by 2 pi, and that's going to be the magenta one. So you'll see both of those, and sometimes one is handier, sometimes the other one is handier. So those are the 2 plots there. It's when we start looping the loop, it's going to be kind of handy to be able to see on the plot where the equilibrium position is as kind of a grounding or a reference point. So I am making, this makes a horizontal line. The vertical axis coordinate of the horizontal line is going to be 0. So it's going to be at the equilibrium point, at the origin. And that's just to make the graph a little bit better. On the omega versus time plot, the angular velocity versus time plot, nothing special there. I just marked where the angular velocity is 0 with another horizontal line. But coming down to the phase space plot, I'm going to be plotting the theta coordinate versus the omega coordinate. So both of these are evolving with time, but I'm not plotting them versus time, I'm plotting them versus each other. So at any given time, the pendulum has a theta and an omega, and I'm going to plot a point there. And then for all these 4,000 times, I'm going to plot 4,000 points. And that's going to be a phase space trajectory. So at any particular tick, that's the phase space of the pendulum, the theta and the omega coordinates. For all the ticks, the 4,000 points, that's the phase space trajectory of the pendulum. And that's everything about the motion of the pendulum. Yes.
Is there like a third or canonical assignment for the x-axis and y-axis?
You mean in theta and omega?
Phase spacing.
I don't know that every time I see it is horizontally is position or angular position, and vertically is velocity or angular velocity. I think that that's just kind of
Chosen.
yeah. I don't think there's I think that's just a common way of plotting
Convention.
or an accepted way of plotting it.
Yeah.
But I don't think there's any physical reason why that's better than the other way of plotting it. We're just used to seeing it that way. So that's, for example, why I'm plotting it that way. You'll notice when I'm plotting the phase space, again, I'm actually plotting it twice here. So I got one chord to plot and then a second chord to plot. And the first chord to plot, I plot the entire 4,000 points of the phase space trajectory. On the second, I'm just plotting I'm slicing the theta and omega arrays. I'm just plotting the last 2,000 points of the 4,000 points of the trajectory. The reason for that is in the first plot, you see the whole trajectory, which will include when we got a driving force, the transient period and the steady state period. In the second plot, where I'm only plotting later times, that's where if we got a driving force, we'll see, we won't see the transient period, we'll just see the steady state period. If I plot them in different colors, I'll be able to discriminate with the colors these two different periods, the transient and the steady state period. So that's why I'm doing these two lines. It's really just down to, I want to show clearly what's the transient and what's the steady state condition on here. Any other questions on that? Yes.
Can I see the code for the modulus? Like,
Yeah.
Like looping it, instead of looping it.
Where was it? This was the code for converting the theta from minus infinity to plus infinity to theta from minus pi to 2 pi. I'm not sure that's the simplest way of doing it. That's the way I ended up doing it.
How does it like? I don't know, I'm wondering how it knows how many loops, like if you're, say, of the 50th entry, how does it know how many?
This second chord, this theta NP doesn't know anymore how many loops you did. The memory is in the original chord. I've still got theta underscore n. I've just additionally got theta underscore NP. If I wanted a third quantity, that was how many loops the loop has the pendulum done, right? That would be an integer, positive or negative integers, say, that would count the number of clockwise or counterclockwise loops. I wouldn't want the remainder here. I would want to just divide here. And the integer would tell me how many positive or negative loops I've done.
Okay.
Okay, so let's just run this as a reminder. This is the absolute simplest case, right? I've got small oscillations, so it's a linear differential equation essentially, and I've got no damping and I've got no driving, and so I should see simple harmonic motion. And let's just take a look at the plot for that. And I've still got to make this smaller now. I'm cutting off the axis at the bottom, but I'll explain it. Old plot from last class in magenta, theta versus time, sinusoidal oscillations of theta. Old plot from the last class in the middle, just omega versus time, the sinusoidal oscillations of omega. New plot for this class, phase space diagram for undamped, undriven, small amplitude oscillations, and it looks like this. Horizontally is the position coordinate, theta. Vertically is the velocity coordinate, omega. So we've got radians horizontally, and we've got radians per second vertically. The equilibrium point of the pendulum is, we defined it when we to be zero. So the equilibrium point is right here, the center of this plot. We released the pendulum, if you remember, from 0.1 radians. So right over here on the right-hand side of the plot, we released it with zero angular velocity. So it literally is this point here, which is 0.1 radians, 0 radians per second. That's the initial phase space of the pendulum. And then the pendulum swings backwards to decreasing theta, decreasing angular position, increasing but negative angular velocity. It swings backwards along this line here, towards the left along the bottom of the curve. Here it will swing through the equilibrium point. This is the maximum of the angular velocity, minus 0.1 radians per second, as it goes through a theta coordinate of 0, the equilibrium. And then it swings far over towards the right, towards the left, sorry. That's again the extreme stream of the motion over here on the left-hand side. It momentarily has no angular velocity. It's at minus 0.1 radians per second, and then it'll swing back along this path here through the equilibrium point again over towards the right. And the phase space trajectory is just this ellipse with the pendulum swinging or rotating around and round in this phase space. And that's what the undamped, undriven pendulum will look like, just this elliptical motion in phase space, where each time it orbits around this ellipse, it just passes over the previous trajectory around the ellipse, because the pendulum is not gaining any energy, it's not losing any energy. It's like a perpetual motion pendulum. It just keeps circling around this point. Let's that's fine. It's not a very interesting phase space. Let's make it a little bit more interesting by going up here to beta, and we'll look at the phase space for the three cases of underdamping, overdamping, and critical damping. So overdamping is when beta is greater than omega naught, and underdamping is when beta is less than omega naught. Our omega naught is 1. We've made it that for convenience. And so if I put in 0.1 here, this is clearly an underdamping case, right? This relatively small damping force. And that's the only thing I changed. And let's go down here. This is the familiar plot of what omega theta looks like as a function of time for the 100 seconds. Omega looks like as a function of time for the 100 seconds. Just to remind you, there are oscillations in the underdamping case. The oscillation frequency is not quite the natural frequency, is the square root, the square of the natural frequency less the square of the damping constant, so it's slightly lower angular frequency, a slightly longer period. There's a kind of an exponential envelope of the decaying oscillations. The timescale of the exponential decay is 1 over the damping constant. So damping constant is 0.1, the oscillations will die away on the timescale of 10 seconds, which is what we see. If I made the damping constant twice as big, then the oscillations will die away twice as fast. If I make them half as big, then die away half as slower. So that's all stuff we meant before. This is the phase space. On the phase space plot, again, I'm covering up, but this horizontal axis is theta, the angular position, vertical axis is omega, the angular velocity. We are starting the pendulum at that point over here on the far right on the plot. This is theta naught equals 0.1 radians, omega naught equals 0. So that's the point. We said as we release the pendulum, it starts to swing back towards the equilibrium point. So theta is going to decrease, but it starts to speed up under the restoring force. And so the angular velocity grows, it's in a negative direction. And so here we see the motion. But this time, we don't execute ellipse after common ellipse. We rather spiral inwards towards the equilibrium point. And this is the effect of damping. This is the effect of underdamping here. We're still oscillating, so we still spiral around this attractor here. But the amplitude of the oscillations is decaying away as determined by the damping constant. So it's a nice way of visualizing the underdamping, the oscillations of the underdamping, and the exponential decay of the underdamping. On this plot, if you remember, we actually were drawing two curves. We're making two plots, so two sets of points. One was the thetas and omegas for all times. That was plotted in green. And then one was the thetas and omegas after starting at 50 seconds out to 100 seconds. That was the magenta. And they're all located at this point. Here by 50 seconds, the pendulum motion, the oscillating motion has died off. And so we just see the steady state here is the pendulum's just sitting there at equilibrium. The damping force has dissipated the energy that we gave the pendulum by releasing it, displacing it, and it's dissipated that energy through the viscous or the drag force. So that's a underdamped pendulum phase space plot. Of course, real easy to look at other cases here. Let's make this exactly one. That's critical damping. That's the special sort of transition between oscillating and non-oscillating motion. So that's a distinct change in the characteristics of the pendulum. And that's what we see here now. Again, theta versus time, omega versus time, the motion dies away on the time scale of the of theta. The phase space plot looks like this. So again, we're releasing the pendulum from theta of 0.1 radian with an angular velocity that's 0. So it's going to start under the restoring force, accelerating back towards the equilibrium point. But it's also, as it starts moving back towards the equilibrium point, in proportion to the motion, there's going to be a damping force, linear damping force. So there's going to be damping. In this case, this is the special trajectory that takes the pendulum back from the original displacement to the equilibrium point in the shortest period of time. That's what critical damping is. And so it just accelerates up to a maximum angular velocity, and then that velocity decays away and it just lands at the equilibrium point there. And that's the shortest, sharpest way to get back to the equilibrium point for the pendulum. It's when beta equals omega naught. If we overdamp, so we increase the damping force, what's that going to do? If I increase beta by a factor of 10, well, the damping force is going to be much larger on the scale of the restoring force. And so there's going to be much more resistance to the motion that's created by the restoring force. So the motion back towards the equilibrium is going to be much slower. And we can see that. Run this again. In these top two plots, you see it takes longer to get back to the equilibrium point. In the bottom plot, you see that look at the angular velocity. Well, they're tiny. So because of the large damping constant, the pendulum has to creep its way back to the equilibrium point. And that's what's happening here. It takes 60 seconds rather than 6 seconds to get back towards the equilibrium point. It's really that large damping is just preventing the pendulum from acquiring any velocity. Okay. I want to move on to the case of a driven pendulum, and we're going to look at onset of chaotic motion. So I want to pick the right numbers for this. So I'm going to numbers that I know what happens. They're not the right numbers, but they're numbers that I've already looked at, so that I can show you what I want us to look at. There was a damping constant that was beta 0.25 I worked with. Then there was I'm going to start with a gamma of 0.99. No, I'm going to start with actually 1.5. And I'm going to change the omega. So this is going to be my first calculation with the driving force. Sorry, this is not very easy to see. These are the numbers that I happen to pick. I do have damping to dissipate energy. I do have driving to deliver energy, infuse energy. I am going to start this out at the at resonance, or at least very close to resonance, within 1% of resonance, and then I'm going to walk away from resonance. And as we walk away from resonance, we'll see different effects evolve. Chaotic effects occur when you have a large driving constant, a strong driving force, being strong compared to the size of gravity. So that's firstly what I'm raging here with the gamma value of 1.5. That's strong driving. When we looked at driving in the last class, we looked at the case of weak driving. We had a driving constant that was much less than 1, so small compared to the gravitational force. Then you don't tend to get chaotic effects. For chaotic effects, we want large driving. that large driving can cause large oscillations. Large oscillations bring in the nonlinearity of the differential equation. So that's kind of our path to chaotic motion, is we have strong large driving constant that creates large oscillations, large motions of the pendulum that brings in the nonlinearity of the differential equation. And then that leads to chaotic effects. That's our root to chaos. Okay, so this is, remember, we're just about on resonance here with a large driving force. And let's just see what's happened here. Here's theta versus time. Here's the omega versus time. These are familiar to us. And also the fact that there's a transient period where things changed in a sort of complicated way at early times, and then there's a steady state at later times. That's also familiar to us. At late times during the steady state, right, the frequency that you'll see is the driving frequency. At early times in the transient period, the shapes are determined by both the natural frequency and the driving frequency. In this case, both those frequencies are very similar. So, you know, we've got omega naught, which is 1 radian per second, and we got omega f, which is 0.99 radians per second. Anyway, so that's the familiar omega theta. This is what the phase space plot looks like. So we're actually starting, the legends covered it up, but we started at same coordinates, right? 0.1 radian, 0 radians per second. So just to on this plot, just to the left of the origin, and vertically at the center of the plot. So right in here, we swing around in this green path here. This is the green path of the first 50 microseconds. So that's the transient period, where I just defined that as being the first half of the plot, the second half of the plot. And then the magenta is where we're oscillating in this steady state period. So phase space shows you very clearly kind of the distinction between the transient period and the steady state period. The steady state period is this sort of oval shaped oscillation. It's not entirely sinusoidal. And the transient period is this period in which we work our way, arrive at the steady state period. Yeah.
I'm sorry, what is basically the mass of your pendulum? Just because I wanted to see it.
So because I defined beta and gamma, I don't need to, they incorporate the math.
Right.
Because, for example, gamma is the ratio of the driving force to the gravitational force. And also beta is effectively a ratio like that.
Well, then, so I'm just wondering, like, my range of radians to degrees is different. Did you, maybe we're just using different gas.
I got a gamma here of 1.5, and I got a beta here of 0.25. And I got an omega naught of 1 and an omega f of 0.99. If we all put the same equation in those same 4 numbers, we should get the same results. Yeah. But I mean, there's a huge number of possibilities for this system, right? Because you've got 4 parameters. So you've got a 4-dimensional world that we're living in. How on earth are we going to explore that? Okay, so that's a strongly driven pendulum near resonance. And we just see a strong oscillations. Notice the size of the oscillations. What are they? it swings to the left and right by more than two radians. So it would have to swing to the left and right by pi radians to loop the loop. So we're not looping the loop, but we are in the world of large oscillations. This is no longer a linear differential equation. And that's why if you look at these oscillations here, they are periodic, but they don't look like they're sinusoidal. That's because of the nonlinearity of the sine theta term. Okay. Well, that was fine. Let's start moving away. This is what I'm going to do in this class. I'm just going to move the frequency. Because it is such a big parameter space, I'm just going to stick with one parameter and change it. I'm going to go to 0.9. Let's see where we're going with this one. And going to 0.9, well, we changed the driving force frequency. We've lowered it by about 10%. But we have the same sort of plot, right? We still have the transient period. We still have the steady state period. We still have large oscillations, but the oscillations aren't large enough to loop the loop. But they're getting larger. This is a little bit larger oscillations than we saw with the right at resonance. As we walk the driving frequency away from the natural frequency, what we're allowing is the driving frequency's force to accumulate and potentially loop the loop. So we're working our way to looping the loop, which will be an interesting effect to see in the simulations, which obviously brings in a lot of nonlinearities through the sine theta term. The phase space plot looks similar. We've got a maybe a bit more complicated transient period. We started at the same coordinate here near the center of the plot, and then we see these large oscillations in magenta at later terms. And we see that they look like very periodic, because it's just a single oval shaped loop. Where am I going? Okay, now I'm going to start picking some weird numbers, which were just based on playing around, right? 7.05. So now I've gone further away from equilibrium, from the natural frequency with the driving frequency. And when I did that, that allows the driving force to build up, and it allows for this effect of looping the loop. So let's start by looking at the looping the loop in these different plots. In the angle in theta versus time, the blue is the original theta coordinate that runs from minus infinity to plus infinity. So if the pendulum loops the loop in the positive theta direction, then that coordinate will increment by 2 pi. If it loops the loop in the negative direction, it would decrement by 2 pi. And if it loops the loop multiple times in the positive direction, we'll get multiple increments of 2 pi, and multiple loop the loops in the negative direction, we'll get multiple increments of negative 2 pi. And that's what you're seeing here. The pendulum is walking its way away from 0 radians to 60 radians because it's looping the loop multiple times in the negative theta direction. So we've created that situation by having the driving force not in phase, not at the same frequency as the natural frequency of the pendulum. The loops themselves, you can see in the magenta curve, this is the function, the quantity theta that I derived from the original quantity theta, where I just allowed its range to be from minus pi to pi with 0 being the origin. So whenever it's discontinuous, that's where I loop the loop from minus pi to pi, going one direction, or from pi to minus pi. And in my cases, I'm going in the negative direction for theta. The loops are, going from minus pi back to pi theta. And so we kind of loop the loop about 10 times in this situation here. And we can see it clearly in that plot. This is the angular velocity. You notice it's a more complicated, it's certainly not sinusoidal angular velocity, right? It wasn't sinusoidal before because we had large amplitude oscillations, but it's sort of approximately sinusoidal. But here it's clearly not sinusoidal. And this is one of the effects of being further away from the natural frequency with the driving frequency. You get a more complicated, but still periodic motion. And we see it in the angular velocity here. One effect you see here is the dashed line, horizontal dashed line, that's zero velocity, because those are the moments that the pendulum is stationary as it's changing the direction in which it's moving. Below that horizontal dashed line, the pendulum is going in the negative theta direction, and above it in the positive theta direction. The pendulum is spending much more of its time swinging in the negative theta direction than the positive theta direction, because it keeps looping the loop in the negative theta direction, not in the positive theta direction. So this correlates with this plot here. Okay, here's the phase space diagram. Again, the green is showing kind of a transient period, and then the magenta is showing the steady state period. And again, we have a distinct transient period and steady state period. Once we get in the steady state period, the path of the pendulum is simply, again, along this line, appearing over here at positive pi, following this trajectory in phase space, and exiting over here at negative pi and re-entering here. And then it carries out this loop again. So in this steady state region here, we're just going around this path and then re-entering over here. Go around this loop in this ribbon and re-enter over here. At the top of this plot, these are these little periods in time in which the pendulum is going in the positive theta direction. At the bottom of the plot, where the pendulum is spending most of its time, is going in the opposite, the negative theta direction. We see that there is a transient period where it's more complicated, but there is a single sort of steady state trajectory at later times. Okay. So that was 7.05. I picked that as a number that's very close to the next number, right? These are barely different. 6.95. So they're different by 0.00, by 0.01. So I've changed the frequency by 1% on the scale of the natural frequency. Right. I want to make this a bit larger. I hoping this one was going to be the bifurcation. I think maybe I got this number wrong. Well,
We have 667.
Yeah, this is me playing around before. 667 is chaotic. So
Okay,
I'm gonna come to chaotic motion, but I wanted to find the bifurcation. It was really kind of a specific point. It's a very quick transition from periodic to the period doubling to the chaotic motion. Now I'm forgetting where I've been. I've been 695. Let's try one more try. Oh yeah, here we are. So this is, about 1% different driving frequency, lower driving frequency from the previous one. I think I did 7.05 for the driving frequency in units of natural frequency. Now I'm doing 0.69, so 1.5%. And what's happened here? Well, we've still got a lot of the effects that we had last time. We're still looping the loop. We're looping the loop in the negative direction. And we looped the loop 10 times, so we still have that effect. We still have what looks like steady state over here, kind of a periodic motion. It's very clearly, it's not sinusoidal motion, but it is periodic motion. The pendulum is still spending most of its time going in the negative direction, negative theta rather than the positive direction, positive theta. And it's a little hard to see on these plots, but maybe we could see it, but it's much clearer on the phase space plot that periodic motion in the steady state, which had the period of the driving period, has bifurcated into a periodic motion that has twice the period of the driving period. So that's period doubling is what's happened here. The pendulum motion in steady state is kind of indicated by the magenta curve here, is one complete period is now, you look here, there's two distinct lines, two distinct magenta lines. So the way to imagine what's going on here, maybe the pendulum comes in along this line. It's going to go on the outer radius here, say. It's going to head out over here. And then it's going to come back on, come through here, go on the inner radius around this loop and head out over there. Now, whether it's, always on the outer radius or maybe on the outer radius over here and the inner radius over here, I don't know. But the complete cycle is two pass across this plot, two loop the loops, because you have to go across these two trajectories. So that's a period doubling. Suddenly the pendulum takes twice the period to complete one complete cycle, one complete orbit. And if you remember, we saw that effect. Last time we saw that effect was in the rabbit population or the human population or whatever it was on Earth or in the field. We saw a bifurcation of the populations from generation to generation. So period doubling. Here we see a period doubling here. So this is, we normally think of this as kind of onset of chaos. Okay, so we've started to see large oscillations, loop in the loop, chaotic effects. Let me just show you if I go further. What I think you've already guessed will happen is full-blown chaotic motion. So here's theta and omega versus time. We decreased the driving frequency, but not by much, by about 10%. But now if you look at the phase space plots and any of the other plots, the theta and the omega plots, this is chaotic motion. There's no obvious pattern to this motion. And this chaotic motion is also super sensitive to the initial condition. If I just change the initial conditions or the parameters by a little bit. So if I go back up here and change this to 668. This is also chaotic, but it is actually not the same pattern at all that we saw in the previous one with a driving frequency that was 0.667 rather than this one being 0.667. So we're in the world of chaos here. So the phase space has given us nice access to picturing bifurcation, chaos, open. In the next class, we're going to introduce what's called a Poincare plot. It's related to the phase space plot. It'll give us further access to exploring bifurcation and chaotic motion. We're going to try and make what we've already done in the rabbit population or in the human population. We made a Feigenbaum plot for rabbit or human populations. We're going to try and make a similar Feigenbaum plot used based on Poincare plots for the damp-driven pendulum. So that's the path in the next class. Any questions on all that?